And it was in the middle of a beef between the administration, the supervisor, and everything, and he was the one who paid for that. Yeah, he ended up defending like November.
So yeah.
It was 1 year he was in laptop, and then he had to prepare his defense for the PhD examination.
Okay, so you have to
It
go
was
back.
like, didn't even recognize the results anymore.
It was a good part of that. I actually think that I have the couple of were connected to how much I work for everything orthopedics, sports medicine. And I emailed like a doctor out of the blue saying, you know, I was confident I'd like to go on and just work somewhere easier, 6 minute walk versus 8 hours flight. And actually, the guy did 10 hours, which is not actually
Let's get started. Okay. So hi everyone. I'm glad some of you noticed the time change. So it's my great pleasure to introduce Dr. Mamou, who is a very old friend.
I'm a lot older than you, let's say.
And also we've been colleagues for about 20 years now. So Jonathan did his PhD at Urban Champaign in electrical engineering, has been working in ultrasound his whole career, and then he was in New York City at the Riverside Research Institute, and he's been working on quantitative ultrasound. He's going to present some of the work he's done, or some of the work you're doing right now. He is now in the radiology department at Weill Cornell Medicine, where he's an associate professor. He also teaches at NYU. I think I said everything that was relevant. The floor is yours.
Thank you for the introduction. It's a pleasure to be here, and thank you for coming so early to listen to me. It's always a pleasure to visit Marie, and sometimes she assigns duties such as this one to give a seminar. So I'm going to be talking about something called quantitative ultrasound, and something I've been doing for nearly 25 years now. It's really the use of ultrasound signal for tissue characterization, which can be applied to many topics in biomedical research. I'll give a brief introduction. I just want to give you some background about the hospital work and my lab in particular, and then I'll talk a little bit about QS, and I picked two projects that are very different but have both specificity, but there are many more that we can discuss. And then I have another baby project which also falls in the quantitative imaging realm, but this is at ultra high resolution, and to the point where we named that acoustic microscopy, and it's done on ex vivo samples. It's in fact done on microscopy slides, so it's very far from in vivo, but it's very similar to optical microscopy, but the contrast mechanism on the image is about acoustic properties. So I work, as Marie mentioned, I work in the Department of Radiology at Weill Cornell Medicine, which is one of the biggest hospital systems in the US, one of the biggest in New York. They have we have about 10,000 employees. There's 2,000 practicing doctors, and that's not including doctors in training, residents, and fellows. And we have a main hospital on the Upper East Side of Manhattan, but they've really been investing a lot in infrastructure. Every 6 months, a year, we hear about some space being converted. It's growing. And the Department of Radiology is very big. There's about 210 faculty, and that includes practicing doctors and also some people like me who only have PhD and only do research. What's interesting in my department, not so much outside of my department, but in my department, it's actually very easy to work with doctors, which is a strength, really. And what does that mean is that actually you can really start a clinical project very easily. You'll find a doctor that's interested, that in fact not only has time, but also gets rewarded for participating in research. And we've been able to do, really, to my surprise, in fact, start new project very fast where we can recruit patients. And to be fair, it's been facilitated by the fact that we work in ultrasound, which is non-invasive, non-ionizing, and risk-free and portable and not very costly overall. The counterpart specifically for me is that I do not have easy access to PhD students. There are a doctoral program in the city of New York, but not in engineering. And another advantage, or we were just talking about this morning, I don't have to teach. If I don't want to, I can. If I want to, but I don't have to teach. And in fact, I'm encouraged to get more grant rather than spend time teaching. And in New York, we have very strong connections with the other hospital systems and universities. So HSS is the Hospital for Special Surgery. It's one of the top hospitals in the world for sports medicine and orthopedics. MSK is very interesting. MSKCC is a Sloan Kettering Cancer Center. They do, of course, a lot of work in cancer, and we are within walking distance, and there is some structure to get money for seeding project, and that worked very well. And Rockefeller, which also includes an engineering department. And of course, we also connected to the main campus, which is in Ithaca. It's not in New York City, it's about a 4-hour drive. And actually through that, I can access PhD students, but I haven't explored too much this possibility because it's not a great environment for the student because you have to take the classes on the main campus and eventually come down to New York to do the lab work. So this is still something being worked out. So I'm part of a lab called the Biomedical Ultrasound Research Lab. There are 2 professors, myself and Jeff Ketterling. And we are, so as I said, we are mostly staffed with postdoc. We have 6 postdocs at the moment, and we don't make a partition of postdoc, but financially we do. So,
Sorry.
That's okay.
I think it's fine without, but it's better with.
And we are always, through connection, and because New York is an attractive city to visit, we often have interns, visitors, professors on sabbatical. We have med school fellows and residents. They can give us a bit of time. They can do some basic analysis and submit the conferences, and that's really important for their degree and their chance to get a good positions. And our lab is almost entirely NIH funded. We can do everything related to biomedical ultrasound, from really technology development, image processing, to some more projects that are directly in vivo in human using existing instrumentations. And my lab in particular, so I'm a specialist of 2 things: high frequency ultrasound, which it means that we're going beyond typical frequency, and that gives you a better spatial resolution. So that's fine resolution imaging. But it comes at the trade-off of a reduced penetration depth. We don't go as deep with higher frequencies. And as I mentioned, this idea of using quantitative ultrasound methods, so taking ultrasound signal to get quantitative information about tissue. We can also call that tissue characterization, and we use that to quantify the tissue microstructure. And so on the back end, we use these techniques to characterize disease in many different ways, depending on the clinical application. In general, when we talk about QS, is anything, again, that we can quantify reliably, that's a tissue property. The idea there is that you're measuring something that has units, that's a real tissue property that does not depend on the scanner settings or who is taking the data. So for example, the cyst diameter has a diameter, it's the true value. So you can make that measurement, that's considered quantitative ultrasound. Color Doppler, as actually here on, you cannot read, but they are actually meter per second related to the blood flow. That's also quantitative ultrasound. Elastography, which probably some of you are familiar with, where you're imaging the tissue stiffness with either shear wave speed or a Young modulus. And this is acoustic microscopy that I'll get to a little bit later. And again, this is an in-plane image of a slide. And so it looks like what you would see with an optical microscope, but the key difference is this, again, is quantitative. This is a speed of sound image. But in this talk, I will mostly focus on QS methods to characterize microstructure and mechanical properties of tissue. So this is the time-tested formula in my lab, at least, to develop new project in QS. So the red part is kind of the constant, even though there are options in there. So we first have to get some ultrasound instrument to get data. So again, we can go from something that we built together. We can use a GE instrument or Samsung instrument, out of the box. We can customize them or if needed, or completely built from scratch, in the laboratory. We can get ultrasound data from simulation, ex vivo, in vivo, humans, animals. And then we do that QS processing. I'll talk a little bit about that. And we get something called the QS parameters, which again quantify the tissue microstructure. And then there's something here that can be a statistical method. It can be simple hypothesis testing. There can be a little bit of machine learning in there that based on some kind of standard or something we're trying to predict. That can be a whole list of a competing modality, all of that. And hopefully that can make a clinical impact. And we've done projects in all of these, either just straightforward diagnosis, or we can monitor healing, monitor treatment. We can get a biopsy to suspicious region in tissue, or even, saying, well, the current standard would be to actually biopsy that piece of tissue, but we are confident this is a benign and maybe we can get away with not doing a biopsy. And so, this is more of the design point of view. So we have an idea of how we can make an impact and how to do that. And that will drive the different methods that we can apply. And this is about 20 years of research on the project in my group. Again, ranging from, this is conventional frequencies. That's maybe 6, 7, 8 megahertz is the standard frequency in basic ultrasound. That's the baby images are made at this frequency. Clinical instrument can get probably close to 20 megahertz, and anything beyond requires specialized equipment. And again, as the frequency increases, the resolution decreases, meaning that it gets better. And so, we've done it essentially everywhere and anywhere. And point out some work that we've done with MAE in the lung. That's very interesting, and you'll probably hear more about this from her in the coming months. And in this talk, I would try to cover one project in vivo in the lymph nodes, in human lymph nodes, and then something on the other side of the frequency spectrum. But surprisingly, we were also able to do it in vivo in humans, in the eye for myopia. And I hope to show you a few slides about the acoustic microscopy. And before I get into the project, some basic slide about ultrasound. So you have a transducer. A transducer takes an input voltage and generate pressure waves. And then if you have a reflector, you'll get an echo signal that travels back to the transducer, and the transducer will do the opposite. It will convert that pressure wave into an electrical signal. And then now when you're looking at the tissue, here is the way as engineer we model tissue is black spheres in the blue background is a tissue. So same thing, you have the transducer send a signal, and the echo from each of this small sphere is collected, and the tissue is more complicated than this, so you get this type of signals. And then to make an image, you have to scan this transducer. That's a single element transducer, but most systems actually use a 1D array, and what it means is that you have actually several of these small transducers here, and you make an image directly without translating the transducer. So really nearly real time to, clinical system probably can reach very easily a frame rate of 60 frames per second using these transducers. And then one more detail about what we call the B mode. B mode is brightness mode, is the very standard grayscale ultrasound image. We take these RF echo signals, and the envelope is detected as this blue curve. And it turns out that the blue curve, as you can tell a little bit from here, lives in the frequency domain in a much lower frequency space. And so it can be sampled very coarsely at lower sampling frequency. And that's, in the old day, was very useful because it allowed you to build ultrasound system that were a lot cheaper by using slower electronics that needed to really sample the RF echo at increased frequency. And these green dots are put together to form one line of the image here in the depth direction, and then the next line will form the next line, and so forth. And so, without going too much into the background in theory, the techniques we're exploiting about scattering, so the way the ultrasound wave interact with soft tissue, is again a simple model with the idea that if you have a tissue that you can model as this one, where you just have random spheres, here you have some clustering, so you see they're closer to each other, even more here. Here, I changed the color just to symbolize that they have different acoustical properties, and here they are bigger. So the idea is that all these tissue models will give you a different ultrasound signal that we can quantify using this QS method. How does it work? I'm just going to go through this slide a bit quick. So there's something we call the backscatter coefficient. The backscatter coefficient is a tissue property. It tells you essentially how a random media, a tissue in this case, backscatter acoustic energy, returns the acoustic energy. So it is a generalized version of a reflection coefficient if you want. It is a tissue property. And the way to compute that is we take a small region of interest, and here are the RF signals underlying this region of interest. And we can compute this using something called the reference method. The goal of this method is to remove, again, system and user dependence. And there's some simple equation to get this backscatter coefficient. And so, again, this is a function of frequency. It tells you how tissue backscatter energy. And really, what you should remember about this is just this is a tissue property. It does not depend on instrumentation. And so what we do with this black curve is that big backscatter coefficient, and we can fit it to different models. And the fit parameters are the so-called QS parameters. So here, in this scattering model that we call the Gaussian scattering model, just because that red curve looks like a Gaussian, we get two parameters, the effective scatter diameter and the effective acoustic concentration. They're related, again, to the size of the structure responsible for the scattering and their number density and acoustic contrast. Or you can use something that is not as physical. We just fit a straight line. So the black curve is the same black curve, but now we're fitting a straight line. So we're not really sure in soft tissue what is scattering. So it depends, on what the backscatter curve looks like, which model is best. And here, for example, would be difficult to make, a guess as to which of these two models is better. But essentially, we parameterize the same curve, and we get parameters associated with the tissue microstructure. And there's something else you can do directly from the envelope of the signal. So again, that you detect the signal, you can show that the way the scatters are organized and the number density will affect the probability density function of the envelope values. And this is really what's shown here is this histogram is an estimation of the probability density function of the ROI. And then same thing, we can put plus or less complicated envelope models that have physical meaning. So for example, we like that homodyne K model that gives us information about the number density of scatters and also their spatial organization, as are they very random or they have some regular structures. So this is in summary the parameters I've talked about up to this point. But again, the idea is that they track the microstructure, they are quantitative, they all have units, and they should not depend on who takes the data, what system is, this is really a true parameter. Think about, if you take a picture with your phone of somebody and you want to know how tall they are, it doesn't matter if the picture is a little bit blurry, if you put the phone far, or, that person height should be that person height. It's kind of what we're doing through this work is to really get a tissue property. So one project that has been very successful is to use these techniques in human lymph nodes of cancer patients. So you probably know that cancer can spread to other organs through the lymphatic system, and sometimes they lodge themselves in the lymph node themselves, and they will develop metastasis in there. And if metastases are found in the lymph nodes, it symbolizes that the cancer is more aggressive and should be treated with more systemic treatment than rather local surgery. The current standard of care for human lymph node is to biopsy suspicious lymph node and look at them under a microscope. But previously, they used to excise lymph node as soon as there was a cancer, and they would excise the primary tumor, and at the same time excise a few lymph nodes, and they would look at them. And we had a project looking at lymph node ex vivo, and the goal there was to help guide the pathologist towards suspicious region, because it was just too time consuming for the pathologist to look everywhere in every lymph node. And here, just, this is a sampling issue. So if you cut it here and you look at that section, you'll see a metastatic foci, but if you cut here, you may miss it. So the idea was to help with that. So that was ex vivo. And the current project, because lymph node are a bit small, we were able to do it very well ex vivo using high frequency. And the idea was to see what we can do in vivo in humans. And it will require lower frequency because, again, we have this trade-off between resolution and penetration depth. And so, but the approach is very similar. And we were somewhat encouraged with the ex vivo results. And we started looking in vivo, and it turns out that it works well, even though the findings are a bit different. And we started this project. So again, here is a case where we use a G system. It's a logic E9 that's actually obsolete for clinical use at the moment. It's in my lab now, so we still use it for research. But it was customized just a bit so that we could get that raw signal that we need for processing. And we have, I think, a few more cases now on this system. And now we have a new grant with a new instrument where we're also collecting more data. But we did what I just described. So we get data in vivo in humans prior to biopsy. So these patients, they've been scheduled for fine needle aspiration biopsy, which is a very, very low risk type of biopsy with a very, very small needles. It's not particularly painful. It does not have too much side effect. And so what we do is we acquire the images just before the biopsy, and then we get the pathological result as the gold standard for training. And so we can do some imaging like that, which is very straightforward. So this is just computing one of these QS parameters and color coding that information on top of the conventional ultrasound image. And here, and obviously, two lymph nodes that were chosen because of their striking contrast. So the same color scale is used on the top and the bottom. And you can see, the top lymph node looks red and the bottom lymph node looks green. So the idea is that this image could be very easy to interpret for a clinician if we can provide them, in real time and so forth. And these are direct images of single parameters, 3 of them here. And of course, the question was whether that generalizes, and it did to some extent. We have, for example, for this is the effective scatter diameter and effective acoustic concentration, and we found them to be very well separated, and that we could classify pretty well using very simple methods. And so, the idea is, in fact, now to take this to the next level where we can plot that, in vivo, or instead of plotting this color information, we can output some predictive value of cancer likelihoods, things like that, that the clinician can, the plan is absolutely not to replace the clinician in this project, is to provide more information. The way the clinician work, they integrate a lot of information from the patient's history and all of that to make their decision as to whether they should biopsy or not. But certainly that could be another tool that could help make these decisions. And completely the other extreme, this is a new project in myopia, so myopia in the eye. And actually this started from people contacting me who were very interested in very simple biomechanics of the eye, because in myopia, so myopia is basically the image is forming in your the optical path is compromised so that the image is formed ahead of the retina in the back of the eye, and so it looks blurry. And as you probably know, when you go to the ophthalmologist every year, they just put, plus or less correction, and then your vision becomes sharp again. And so, when somebody approached me about myopia, I really thought that was not a very important disease to study. It seems like a minor annoyance. I was aware that a lot of people were myopic. That's clearly a very prevalent disease, but I didn't think it was very major. But it turns out that it can happen that the mechanism of why the eye keep expanding, which is the key reason why eyes are becoming myopic, are not very well understood. And we know some things is happening in the posterior sclera. The sclera is the white part of the eye. That's what gives its mechanical strength. And so they were very interested in, what's happening in the back of the eye, and can we predict the evolution of myopia and questions like that. But also, they patiently explained to me, probably like they've done with other people who are not aware of the state of the art in the field, that as the eye expands, it can reach a point where it's so mechanically compromised that it can actually buckle, and they call this a staphyloма. And as you can tell here in this cartoon, if it happens close to the optic nerve, you actually will lose vision. And so now, suddenly, you completely shifting gear because everybody is becoming myopic, and there is a mechanism by which you can lose vision. It is a very major disease. It's actually a pandemic, in fact. And the numbers keep increasing in terms of prevalence. And so, the latest prediction are not great. It's about 10% of the population by 2050 will be not only highly myopic, but at risk for these things to happen in the back of the eye. So now we go from a problem that seemed completely minor to something that's actually we should, tackle right now before it's too late. And so, what do we know? Well, there is a lot of mechanism happening in the posterior sclera that explain why the strength is essentially less load-bearing and the eye keeps extending. We still not understand the messaging, why the prevalence is increasing like that. It's probably multifactorial, people more on their phone, less outside, work more, things like that. But on the mechanical side, there's clearly a lot of signaling going back and forth. And so, all of these things, when I'm looking at that, I'm thinking, wow, it does look like ideal target for QS because it's really, there's only collagen fibers essentially in the sclera, the white part of the eye. And so if their structure is affected, it's something that should be able to sense with these techniques. And then, there's this slide that got me very excited. It's really the different structure. It almost looks like that plot I had before, right? When I was explaining the fact that these different random media will give you a different QS signature. With a very big caveat is the resolution here. This is 300 nanometers, so it's nowhere near what we can sense with ultrasound. But still, I think the way an ultrasound wave will interact with this medium, even at wavelengths that are, obviously in the micrometer range, should be affected, and that's something we have been looking into. Okay, and so some of the first studies were in the posterior sclera in animals, in animal model. This is actually a guinea pig eye model. And we demonstrated that something very simple, and it was very encouraging results. So we measured in the back of the eye, we did the QS analysis, and what you're seeing here is by measuring the microstructure of the white part of the eye, we could somewhat, not, it's significant correlation, but not very high, predict the vision correction. So what would be needed for this eye to see sharp, right? Or its actual length, so how much has been expanded. So this exercise is useless in terms of myopia treatment because we can measure that by much more accurate methods. But the fact that there is some microstructural correlation between, again, the white part of the eye and how big is the eye, or how much of a refractive error you have, it was very novel. It's a very interesting finding. And so the next step, which was essentially a double leap forward, we decided to go straight to humans and to go to very high frequency because the sclera is only about 500 micron thick. And the compromise there is that we cannot access the posterior region of the eye. So there is some hypothesis that the anterior sclera is also affected by myopia, but it was not as strong. And so that project really made these two things. Are we going to measure straight in humans and a region that we're not sure is really affected by myopia? But that's the best we can do. And if we can do it, it's going to be very meaningful. So not too much about the electronics here, but it turns out that except that it's extremely challenging to make high frequency transducer to optimize the electronics and everything. This is as simple a system as you can find. It does not form images. It's a pen. So you just put it on the eye and it gives you a signal, and we analyze that and explain how. This was built all in the lab using off-the-shelf component. And we have to design a few circuit board and everything, but again, it's within our skill set. And the system uses a desktop computer and another box, and so it's mobile, let's say not portable, certainly not ultra portable, but that was not the focus. We design custom software, and I'll explain how we analyze data here. This is the collaborating site in Singapore. So the project went to Singapore for because in Southeast Asia the prevalence of myopia is very high, and actually this is a long-time colleague of mine who used to be a doctor in New York and is an excellent clinician scientist. But it turns out that his wife is a complete rock star, and she was given a job in Singapore that she could not refuse, so he had to go there. After a while, his medical school degree from the US were recognized, and he can exercise medicine. And now he leads a clinic of high myopia patients, and he has access. I mean, when we went there, so this is Cameron, the postdoc in my lab that served as the guinea pig because we cannot take picture of enrolled subject. But we went there for 3 days, and we scanned over 100 patients, so they had organized all of that. So what do? We put the pen on the white part of the eye, nasal and temporal. So nasal is close to the nose, temporal close to the temple, and we do it for both eyes. So we have 4 measurements per patient, 2 on each side, on each eye. And then for each measurement, we do 2 types of scan. One is what we call a virtual B mode scan. It looks like this. So we ask the clinician to move the probe slightly to actually get data that looks almost like a B mode image. Why is it not a B mode image? It's because actually that axis is not a distance. We have no idea how much he moved. This is actually time, how much we pulse the transducer. And we can use this to do the backscatter technique. And then this one is, we call that the passive elastography scan, and I'll explain how we do it. But here we do the opposite. We ask the clinician to not move, to stay static. And it turns out there's a lot of small shear wave propagating around the eyeball that we can track to get actually measurements of the stiffness of the sclera, which of course we think is very important for myopia. So, here it explained a little bit of, we wrote some algorithm to do this almost automatically, but the point is at the end we get a BSC, that's the black curve again. Just your attention, to the frequency of this transistor. The bandwidth is really 60 to 110 megahertz. So again, that's 1 order of magnitude more than the typical baby picture, if you want, the typical clinical ultrasound system. And same thing, the envelope. So that's, the techniques are already explained. And so we just pile up the data that we've taken where the lines look different, essentially. And to the contrary, for the passive elastography, we want lines that are highly correlated and look very similar, where we can really track very small vibration. There is some very small shift that are due to a diffuse field of shear waves in the eye. And we can compute the displacement, and from that we can compute the shear wave speed as a function of depth. So this is the same table. I just wanted to say we have an additional parameter I didn't talk about that is related to the tissue stiffness. And again, for most people, the idea that the eye can expand is because it's becoming softer, but of course, it's a more complicated phenomenon. And so the hypothesis of the grant was really that the QS parameters that are sensitive to whatever myopia is doing in the sclera. We know it's in the posterior region, it's happening, and we're wondering if it's also happening in the anterior sclera. So again, we scanned about 85 subjects. I think we actually are closer to 100 now. And they come to the clinic in Singapore, and they actually have a lot of other tests done, including measuring their refractive error. So the refractive error is the needed vision correction that they would need to see sharp. The actual length, which is the length of the eye. The two are correlated, but not 100% correlated. So you can have refractive error just because of your lens also. So you could have an eye that's a normal length, but there's some problem in your lens beyond your iris, and that creates focusing ahead of the retina in the back of the eye also. But most people with high myopia will have both, a large refractive error and an increased action length. So again, nasal and temporal, both eyes, so 4 regions per patient. We compute the vascular coefficient and the envelope statistic and the shear waves. And for now, the first analysis, we average all over the place, and we're really getting just these 9 numbers per eye. And again, the result is a little bit similar to the ex vivo, except that, remember, this is anterior where we think there is less going on. So we have significant correlation, but not very strong. And in fact, this is, predicted refractive errors. That's a discriminant analysis based on the QS parameter to predict the true refractive error. And here the same thing for the action length. And so same thing, 0.38, 0.35, so not great, but still significant. So this again demonstrates that there is some information shared in the anterior sclera, big news, that concerns your vision correction. So how much you need to see sharp, which has mostly to do with where the light is focused, so has nothing to do, really, the two measurements are independent, but they share information. That's what this is saying. Again, the same point I made earlier, this is also not what this instrument is intended for, because you can get that true refractive error using very simple techniques, which was actually the case in this human study. And so, somewhere you can land on this, right? So we are a little bit surprised and happy. So we can demonstrate that there's some changes in the anterior sclera related to myopia, and we can measure them with this sophisticated QS technique. On the other hand, we can also say that the fact that the correlation is not as high as it could be means there is some other information in the QS parameter that could potentially be exploited for really the clinical target is prediction, is to say, this eye is very myopic, but it's going to stay like that. It's still solid. It's not going to create this problem of staphyloma in the back of the eye versus this eye is like, well, they, moderately myopic, but it at risk. It looks like very compromised and something may happen. So this is the end game of the instrument. And so how do we get there? Well, it requires longitudinal studies. So actually these patients, we scanned them again last year. So that's 1 year of that time. We're scanning them again this year, and we'll present some results. And I have a little bit more statistics, but I think I can go quick through those. So we classified patients into 3 groups, actually 4 groups, based on their refractive error. Yeah, maybe this is not completely clear, but so there's a control low myopia and high myopia. These are completely split based on the refractive error. And then there's something called pathological myopia, which is regardless of refractive error if they have a staphyloma in the back of the eye. So again, this outpushing. And so you can see there is absolutely no overlap in refractive error between the first 3 groups, but there is some in the 4th group because it's pathologic, it's a disease, it's not a state of your eye. And you can see, it does not cross to middle, so it's mostly highly myopic eye that will develop a staphyloma, but they're not completely separated in terms of range. And you can see the actual lengths. There is some overlap, so as I was explaining, it's highly correlated, but it's not 100% correlated, so there's kind of 2 causes of myopia. And just briefly some results. So same thing, we have a lot of overlap when we're trying to predict in group, and we see something where most of the time it increased between the first 3 groups, and then pathologic always behave very differently. And so it's, slowly increasing, and then this surprisingly, at least for this parameter, looks a lot like control, which, not what you would want. So since then we improved this, and we have other tools to first classify an eye as to whether he has a staphyloma, and then if he does not, then we can use this trick, and so it's a bit better, but it is very interesting, and again, more data is needed to really look at that. So the instrument is working in human, as I explained. We can get RF data really built from scratch. We showed some correlations that were at the same time significant but not very high. And we were able, to some extent, to classify the myopia group. I didn't talk too much about the automatic processing, but this is important because the clinician will want the results, but also something that we've wrapped up in this automatic processing that I didn't discuss is actually during this data collection in Singapore, we were in the room giving feedback to the clinician as to whether his scan was good. And of course, that's something that should be displayed on the system or make a beep and tell him you need to do this or do that. And as I said, we are now analyzing data we just took this past October, and this is really the key. So now the question is, provided the QS parameter at the visit in October 2022, and also whatever age, gender, even refractive error at the first visit, can we predict the evolution of myopia in October 2023? And so we have some evidence that it works a little bit, but 1 year for adult patient is not a big change in myopia. So we don't have a lot of patients in our group that got worse, but we can predict them. And so we're going to go back again this year to take a two-year data point and so forth. And I want to get briefly to this. This is my baby project. I like this one. This one has the most engineering fun stuff, and potentially the least, but the less clear connection to biomedical research directly, let's say. This is coming from an institute that found technology grant development without the need for a biological hypothesis. So the idea is that you're developing instrumentation that could be used for biomedical research, but yet you're not doing biomedical research in this grant in particular. And that's cool for engineers that we always have good ideas, and then some to get funding, we kind of have to market them for a clinical application, except this mechanism does not directly require that. So one way to understand quantitative acoustic microscopy, before I explain how it works briefly, it's imaging the same sample, the same orientation as any kind of optical microscopy. And it forms images in the same plane. You can see example here. What's the difference is this, this color scale, the contrast mechanisms is what the pixel value mean. And so the pixel are not only quantitative value compared to a stained image in optical microscopy, and they also describe true tissue property. In this case, for example, something called the bulk modulus or the ultrasound attenuation. So how does it work? Well, we use ultra-high ultrasound frequency, even beyond what we use in the eye, so beyond 100 megahertz. We call that a C-scan as opposed to the B-mode image. So C-scan meaning that we imaging in plane instead of in depth. It turns out that acoustic microscopy is very, very well established in non-destructive testing. So there is, companies like Motorola that make chips. They have instruments that will scan their chips very fast and find micro cracks and things like that to discard potentially failed microchips. But for soft tissue, there is some clinical instruments, some instrument that you can purchase up to 100 or 200 megahertz, but nothing beyond that will make image, and they're almost ready. Just put your slide and push a button. So it's also somewhat established in soft tissue. And we, again, could use it in myopia, but I'm not going to be talking too much about this here. And so we have designed this instrumentation up to 1 gigahertz center frequency. So that's times 10 again. So it's 100 times greater than the baby picture again. And that gives you a resolution in the micrometer range. In fact, it probably should be a smaller than equal sign. So the resolution is smaller than 2 microns. And so we can make quantitative images of acoustic impedance, speed of sound, or acoustic attenuation, and some other parameters like the bulk modulus and the mass density, for example. And the system is also conceptually simple. There's a single element transducer, there's a glass slide, and we translate, raster scan the transducer on top of the glass slide, and then we do some processing to form the images. I'll talk briefly about how we do that. And then that's the concept. The concept is easy, but putting this together is a complete engineering nightmare. So first, it requires very precise motor stages. We're stepping, in fraction of micrometers. Any vibration will create problems. Even, the temperature in the room has to be controlled and measured. It requires extremely fast electronics. So, if you are exciting a transistor at a gigahertz, you need to sample it at least at 5 gigahertz. So you need to buy very specialized digitizer cards. And you can see this does not get designed. This is the receive line of the receive transmit line. So to amplify and condition the receive echo to get something that look decent, there is some inline filters. It's low noise amplifiers, in fact, low noise amplifiers. And this is called good engineering trial and error. So you put your system in, look at your echo signal, what it looks like, and you put different things that you think will improve the signal quality. And then once you reach something that looks optimal, you take picture, you document everything, and you don't touch anything. But it's really not fun. And the reason why it's so complicated is because at high frequency, electrical impedance might not be exactly equal to 50 ohm. And remember that small capacities that are part of your transmission line gets multiplied by a gigahertz, and that becomes crazy in terms of reverberation in the line. Also, at this frequency, the cables will start receiving radio waves also, which can create noise. The transducer active area is much smaller, so you have much lower signal-to-noise ratio. So, this is actually the only instrument in the world going to a gigahertz, and it doesn't look like much, but it's really the state of the art in a way. And then, a key component of this is this very fancy transducer. So we have 3 different transducers at different center frequency. If you want to understand this, they are essentially the magnification factor that you would have on an optical microscope, right? So you rotate. So every, from left to right, you increase the spatial resolution by a factor of 2 every time you do that. And as you do that, the cost of the transducer increases, the sensitivity to vibration and temperature increases, the need for faster electronic increases. So basically, the higher the frequency, the harder it is to put together the system. And we can scan these resolution targets that are also standard for optical microscopy, but it turns out that the ink on the targets also has different acoustic contrast, so we can see it. And here, and you have, this is a kind of a fractal structure with different groups and different spacing between the bars. And here I'm just, illustrating that if we're looking, bars that are close to 2 microns, we cannot see them at 250, which has a theoretical resolution of about 7 microns. We cannot see them very well either with the 500, and then we can confidently say that the resolution is better than 2 microns, or at least 2.16 microns at a gigahertz. So how does it work on the signal processing to get these images? I'm not going to explain the inverse model, but the forward model I think is easy to follow. So if you consider the sample, you have a glass slide, and then you have the sample tissue, which is very thin on top of the glass slide. And we're using saline, again, temperature-controlled saline as a coupling medium. And you have the transducer in the case where you're just on top of the glass slide. You're just getting one echo that would look like this. And if you go on top of the sample, you're getting 2 echoes, one from the water sample interface, as you can tell, arrive earlier in time, right, because there's less travel distance, and one from the sample glass slide interface. And it does not arrive exactly the same time because actually in the sample, the speed of sound may be different than water. So in this case, the speed of sound is greater than in the water, and the signals arrive earlier. So the idea is just that the first signal amplitude, so the amount of reflected echo at the water sample interface is related to the acoustic impedance of the sample, so we can inverse that. Again, the time of flight, so the time it takes to propagate, is related to the speed of sound and the tissue thickness. So there's 2 unknown and 2 equations we can get to get that. We don't care too much about the tissue thickness, but it's an intermediary parameter that we have to get. And then the attenuation has to do with the frequency content of this signal, and that takes also a little bit of work. And just some images to show you what it looks like, and I'll stop here. This is same sample scanned at 2 different frequencies. Here is 250 and 500. These are I samples. So this is amplitude image. So this is just when you take the maximum of the echo signal, which It's just a way to see the morphology, but it's not quantitative. It depends on too many parameters, but the point is that it looks sharper. At 500 megahertz, you have better resolution. And then you can convert this through processing to a speed of sound map. And you can see not only you have better spatial resolution, but there is also something called dispersion. And usually at the higher your frequency, the faster the speed of sound is. And you can see there's more yellow pixel in the higher frequency. And here's another example. I think this one is from a human lymph node. And just quickly, a couple of images using the gigahertz system. So this is, again, whole sample, about 200 microns scale bar here. And you can see 501 gigahertz, and you see the same effect. It's like the optical microscope, the resolution. It's not because we can go to a gigahertz that we should always use a gigahertz. It depends on what you want to see. But the capacity of doing that it's not easy. And here are the quantitative images. So same thing. Here is acoustic impedance and the attenuation. And the attenuation also is known to be nonlinear, so it typically will increase faster than the ultrasound frequency, and you see more yellow pixel and higher values in the scale. And so this modality. So when I show these images, a lot of basic science researcher will come to me and say, "Well, can you measure our sample?" And the answer is, well, it takes some work to use the instrument. It takes some time to be trained, so that's a limitation of the technology. And the reason they're interested is because there are cases where the HNE staining, or 2 photons, or second harmonic imaging, and this kind of mode in optical will not show contrast between tissue types that they know should be different or behave differently, and so this sometimes can provide evidence. And in the case of myopia, which I did not show here, we have published several studies with just numbers, showing that arguing that the myopic sclera was, thinner and also softer in a way, less load bearing, but we can do it at a very, very fine resolution compared to measuring a bulk value for the tissue stiffness. And so the goal of this grant is to bring this technology to a microscopy suite where the instrument could be used by an untrained user with the push of a button. And we have several different techniques to get there that we're looking, including post-processing. We're doing some compressed sensing. We're trying to deal with buying very crappy motors, which is really fun. So the idea is that you can ask a motor to make very precise tiny steps, or you can buy a motor that will not go where you want it to go, but it will tell you where it goes. And what it does is it creates randomness in the spatial sampling, and actually we can use this a random position to reconstruct an image using fancy compressed sensing methods, and that can reduce a lot the cost of the instruments. It just need access to the encoder position on the motor, and this kind of fun stuff. But there's a lot of different axes that are kind of plug and play in terms of what we can do. But I'll stop here. And just to say that we collaborate with a lot of people in a lot of different places, including here and further away in the world. And that's many of these projects, again, are, in particular, the project with the group in Singapore was a complete success because they're extremely well organized. I mean, you cannot imagine recruiting 100 patients over 2.5 days and having that work out and planning the patient every 15 minutes when we have no idea how long it will take to take the data. Anyway, stop here. Thank you for your attention.
Thank you, Jonathan, for this great talk. Any questions?
Yes, we've done. It's a little bit here, but yes. This is the prediction. This is actually done by combining the different QS parameters.
Have you looked at not averaging both, the main
because
the buckling, you would imagine, would happen more if there is
An extreme value, you mean? Yeah, I think we need.
Difference
Yeah,
in both sides.
we on.
The pressure is no.
Yeah, so that's what I said. I think based actually because of this one, right? I think when I saw that first result, not only even though the mean are increasing, I think they are statistically different, but obviously you cannot classify right with this type of overlap. When I saw that, I thought, well, first maybe let's see if we find some simple algorithm like you suggest that split the eyes in two groups, right? This one has staphylomas, this one doesn't, and then in the group that doesn't, can we actually classify using different techniques? But again, this is not important. The question is whether we can predict the future.
Yeah, sure, but maybe you can predict the future better if you don't average the
No, you're right.
sides of
You're
the
right.
eyes.
You're right.
Because mechanically, I would imagine that
Yeah, it could already be weakened somewhere. That's what you're saying, and then that's where the staphyloma. Yeah,
that's
absolutely.
What
Yeah.
eventually, and maybe you can calibrate it better. Yeah.
Yes. So, very good question. Wow. I didn't talk about the inverse model, but it has to do with the inverse model. So it has to do with your ability to separate the first and the second signal. And this first and second signal separation is 2d, the thickness of the sample, divided by the speed of sound. That's the absolute time difference between the two signals. And so the speed of sound, with soft tissues, you can, use like something like 1500. And so then it has to do with the actual resolution of the system, right? So the ability to separate the two signals depends on how many cycles your pulse is composed. In this example, there's only like 1 or 2 cycles, and can easy. And as you decrease the thickness, they will overlap in time and also in frequency, so they become harder to separate. We actually have, I have the state-of-the-art estimation algorithm, and then I just got scooped by somebody who improved it slightly. And I think we can go to about 1.5 wavelengths. So the separation between the two signals. And it has relevance. I think maybe that's why you're asking this question, because we actually can do the acoustic microscopy and then send them for staining and get an HLE image. And in some of the older study where we needed like a thickness of 10 microns or 12 microns, when you stain an image with the optical microscope, the image is blurry because it's too thick for the optic. But now we can image at 500 megahertz, 3 or 4 micron thick section, which is standard also for histology.
Any other questions? Yeah. For the myopia study, when you collect your images, do you have to do image registration to compare like image to image, or is there a different one?
So we don't do imaging. We only acquire lines of data manually. Do you mean to know where we are in the eye? That's what.
Because you said you were comparing like different signals one to another. On one of your slides where you had the two different cases that you were cross-comparing.
The P and you're talking about this?
Yeah.
Okay, so this is a pen. It's pulsing at what we call a PRF, a pulse repetition frequency. So there is a clock that says pulse, 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 pulse very regularly. And then we record with buffer, and we send to the. So this again, this is line number. So this is line number. So how many lines we acquired, and between two lines, I think we have a 8 kilohertz PRF. So it's 1 divided by 8,000 is the time between two lines. The top scan, what we call the virtual B mode, or the scan we use for the BSC, we ask the clinician to move by himself, and we have no special information about how much is moved. Here. And that creates this. And in the P scan, we do the opposite. We want to stay at the same position because we want to track these tiny shear waves, elastic waves, to estimate the stiffness. So we ask the clinician to stay as static as they can, and actually, surgeons are very, very good with their hands. I couldn't do this, even though it's like a fraction of a second. You cannot see it here. We also had to decide how to do the measurements was not clear. Here he has a piece of foam where he puts his elbow, and so he's very stable with the patient in the eye. So if you're asking exactly which portion of the eye we measured, well, the ophthalmologists know where it's going, but then we're talking about 10 micron resolution, so of course it's not consistent exactly from eye to eye, but there's no co-registration step. Did I answer your question?
I have one more. It's more of a philosophical question.
Okay.
I guess. So when you introduced the BSC, you said that the Gaussian fit was more physical than the linear fit.
Yeah, they're both wrong. I guess you're right. So there's no, let's put it this way, there's no physical interpretation to the linear fit, whereas the Gaussian fit is scatterers that have, well, actually, if we want to go into the detail, the law of large numbers, if you had a distribution of scatterers that are hard spheres, or finite dimension sphere, they can converge to a Gaussian form factor, which is not what we're arguing. But otherwise, you're right. We're talking about scatterers that have infinite tails in impedance, and so everything converges to a Gaussian. So yeah, maybe I should change my wording. And the part that's actually also it's the other models that are more complicated to fit and more realistic. Yeah. The form factor, the shape factor, whatever, it's very close to a Gaussian also. So maybe that's why they have almost the same shape, but they use this, Bessel function and all that. So it's harder to optimize. Although people do it now because computers are faster, but in the old days, the Gaussian was easy because it's just fitting a line.
Any more questions? Well, let's thank the speaker.
Well, thank you.
And sorry for the students who came attend and who didn't get the message about, I'm sorry, yes, I'm not sure what happened. We got changed in one website, but not in the other. Yeah.
Especially not on Google.
I know, I learned that this morning.
Also, right now on Google, the passive method has not silent, right? So I'm just getting that.
Yeah, that's not great.
Oh, that's not gonna write. Is there one from the other? The patent finds us at
So, guys, I have to go to class. So Jonathan has a meeting with Dr. Chiang at 5. Yeah, because I have to go to class and then you ask Dr. James to walk him to Omer, or I can share that with you. I'm going to share.
Oh, cool.
Yeah, I guess I'm going
I'm going to share his schedule with you. We'll have to run. Jonathan? So my students, you have a meeting with Shining in 30 minutes.
Okay.
But I have to go to class now.
Okay.
So they're going to take you to get coffee.
Okay.
Whatever you need. Or
Yes.
bathroom, or do you need to to my office maybe? You want to go to my office? Whatever you want.
I don't know where is that meeting. It's far from you.
It's everything in the same building, except
Okay. But we cannot sit down where we're taking coffee. So 30 minutes to meet Shaolin. So I don't have any downtime. Right? When would I go to your office?
I'm busy in class.
Yeah.
No, you don't need the key?
It's a complicated question. Do you need your key?
I need it now to go get my notes, but then that's it.
Why doesn't it walk to the office?
Sorry?
Why doesn't it walk to the office?
I'm going to class.
We have to go to your office first.
I'm going to my office first, but I can leave the key or I can let you guys go get coffee.
Let's go get coffee.
Okay, so you gotta get coffee. You keep the breakfast?
No, yeah, there's your thing. What time you need it?
I need it at 11:30.
But where would you find me?
Okay, it's okay. I'll eat it later.
So many logistics problems.
Yeah, I was like, I was late. It was cool. Yeah, some guy. I was a little disappointed. So they were like, "Yeah, we're gonna bring you screw up. You're gonna go to your food." We were like, "Cool." Well, so we went out to get it. Just like one interview, one news guy.
It was already weird.
Yeah, he had like a camera, and he had all the stuff, and then and he interviewed you, man. He was like, "That's it. That's like all I need."
Any mile that still runs is a mile that we have won.
I mean, I guess we weren't like pushing it, but so yeah, so SUMED will be on TV, and the rest of us will be kind of like yeah, like the B-roll footage where like we're doing stuff, but we didn't get it. But yeah. Oh my god, I found that dog. Those two dogs. I gotta get dog treats for the back of my car because the last week we drove up there. I found a farm dog that we got now, and I know, right? And that one wouldn't come to me. So I was like, okay, clearly, I got CJ and my sister in my car this time. So like, I should get some dog treats just to make it a little easier on myself.
I love that the second you called the mom.
Yeah, like, I guess when I get unknown numbers all the time, but it's always spam. But I guess she was like, breakfast, coffee, ice cream.
Yeah. You got the code?
The code's right there. They wrote a new one.
Oh, they have a new one?
Yeah, somebody just came out with a Sharpie.
Oh,